I'm Langxuan Su. I'm a PhD student in Duke Math. And well, today I'm going to talk about my recent work on a large deviation approach to posterior consistencies in dynamical systems. And this is a joint work with my advisor, Cheyenne Mukherjee. And okay, so let me just begin. So this is the table of contents of the talk. I'm just going to probably just talk about the first two parts, and the last part usually will be over time, but this one is not so important compared to the first two. Okay, so let's start with some background of the problem here. So first we want to look at the classical problem of Bayesian inference. Basically, well, first we have a prior probability on the space of parameters, and we observe some samples that's maybe generated by one of the parameters. And then we want to calculate the posterior distribution on this parameter space by just using the Bayes rule. And so there's a problem called frequentist posterior consistency, which basically says that like how do you justify this Bayesian procedure? So is this posterior is really a good one? In other words, maybe as you observe more and more samples, does this posterior distribution concentrates on maybe the true parameters? Yeah, and this is called like the posterior consistency, and it has like many like different mathematical definition. Where some people may study the convergence of the posterior distribution as a measure, or maybe just as a density, or maybe only consider the mass, whether it concentrates on any subsets of the parameter space. But there are many different notions of consistency. And yeah, so if we consider these samples, like the underlying distribution of these samples, there are many results they are proved when the samples are coming from maybe IID processes, proved by Duke with maybe some nice application of martingale theory. And also there are many results on when the samples are from Markov chains, and also like Gaussian processes. When you just look for the work of like these people, you can see a lot of posterior consistency results for samples coming from this relatively simple processes. But if we consider samples that are from maybe dependent processes or even dynamical system, in that case, actually there's almost no results on posterior consistency. Maybe just one result from Charlizy, and just very hard to find like the results for zero dependent policies and dynamical systems. And okay, so in this work, we also consider something called the generalized Bayesian inference, which means that sometimes we don't have access to the likelihood because we don't know what is the true data generating process when you have a parameter, and you don't know how to calculate the likelihood. But sometimes we still have the loss function, right? So we can measures the loss, maybe the distance, something like that. So in that case, we cannot use the Bayes rule to calculate the posterior distribution, but we can still calculate something called the generalized posterior distribution based on a loss function. So it's given by you integrate the exponential of the minus loss respect to your prior distribution, and then you divide by the normalizing constant. So this one also gives you something called the generalized Bayes posterior, and in the sense that if you just take the loss to be the negative log likelihood of y given theta, then you recover the original like Bayesian inference. Okay, and yeah, and there are also connections with what's currently a very popular topic, maybe in machine learning, the variational inference. In that case, people want to try to, so instead of finding the true parameter, they may want to find the parameter that minimize some costs, like for example, like solve some variational problem. So in that case, they call it the variational inference. And also people sort of develop quantitative bounds, like finite sample bound of that, that's so related to tag base in that area, which we are currently still exploring the connection, but that's some of the related area that we can think of. Okay, so let's go to the exact setting. So again, we want to do like Bayesian inference to like on dynamical system. That's our general goal. And here I give you like the stripped down summary, like ignoring many of the very technical definitions about our setting. So basically we have just these 4 components in our setting. The first one is the parameter space and a prior distribution on the parameter space that sort of gives you the prior belief of the distribution on the parameter space. And we have a system that sort of generates the samples. Right? That's we use the letter Y to denote the samples. And then we want to sort of maybe learn or do inference on the parameters, maybe find out the true parameters of the underlying data generating distributions. And for that we use a model family of processes. So in the back of our head, we have a family of model processes that's parameterized by theta. And this family can be maybe a family of Markov processes. So we sort of guess like what is the underlying distribution of the samples. And we want to find like the best parameter theta, or the best process among this model family to sort of approximate this approximate the samples. And then to measure like how well we can approximate the samples, then we have a loss function. So given theta and the underlying state x and the samples, we can measure the performance of how well this parameter and this underlying state approximate the sample. So a very typical example is like the hidden Markov model, right? So this is x is like your hidden states and your parameters, and then you have samples generated from the hidden Markov model. And you can take a loss function to be the negative log likelihood, and you just go back to your usual Bayesian inference. Okay, so this is the 4 components we have. So from this, we want to develop a generalized posterior distribution. This is given by the following, just as I mentioned in the previous slide. So for any subset of the parameter space, you first integrate your exponential of your negative loss function with respect to the prior distribution. So here you take the expectation with respect to the hidden states, and then you integrate the parameters with respect to your prior distribution. So in that case, and you also divide it by a normalizing constant. So here you obtain your generalized posterior. And again, if you pick like the loss to be the negative log likelihood, then you recover your usual posterior distribution. Yeah, and this loss like L with superscript t, just you accumulate your loss up to time t. So which is given by here. So it's a summation of your loss function for the path x starting from s to infinity and the samples at time s. So here we don't just include the hidden states at s, we include the whole path, because in this case it's more natural to consider the whole path when we consider dependent processes. Right? Yeah, because when we have dynamical system and dependent processes, a single point, a single time step sort of does not give you like information so much, but you need to look at maybe the path to see how the dynamics involves. It's not like IID where, or just Markov processes where you have very simple dependency structure, then you can only look at maybe 1 or 2 time set. But here we consider like the whole trajectory. Okay, so any questions for the setting here, the strict time setting? Yes, I see someone raised.
Yeah, so I'm slightly puzzled. So your loss function depends on the infinite future.
Well, yeah, I mean, in principle, in this, yeah, if I write this way, it depends on infinite future, but later on we can assume that it only depends on maybe finite amount of steps, but arbitrary large. We don't have like fixed order of dependence.
Okay, thanks.
Yeah. Okay. Okay, let's move on. So yeah, so this is the stripped down version of the setting, just to be more pedantic than necessary, and I'll probably give you the precise mathematical formulation, which is not very important, but just to be precise. So in this work, we actually consider both discrete time and continuous time horizon. So we can yeah. So yeah, and then our observed system, like the system that generates the samples, is formally defined as this. So is there a hand raising, or just you forget to put down your hand? Okay. Okay, so this observed system is the system that generates the samples. So formally, just you have a space which is Polish, which is just a nice space, and then you have the dynamics here. So the maps that give you the dynamics on the system, and you have a measure on the system, which is an ergodic measure. So we make this assumption of ergodicity just to well, just to have the interpretation that if you want to observe some statistics from just one trajectory, then ergodicity is sort of natural, because like when you have an ergodic measure, then any almost sure any trajectory will capture like the average statistics of the system. So it's a natural assumption. And because we assume that actually the system is deterministic, well, or you can include like random processes, but for the sake of generality, we assume this can be deterministic. Then it means that when we observe a sample Y, we can also observe the whole sample path. We don't necessarily know the underlying dynamics, but when you want to have more samples, you can always ask the system to give you to generate the whole trajectory for you. But this is just a very pedantic description of the system that generated the samples. So then we also so the second component, remember, of the framework is to have a model family. And here our model family is given by this system. So in this case, we made a choice that the space is the space of continuous paths from time to any to some like Polish state space. Basically, we want to model the observed system using like stochastic processes that sort of defines on that sort of has the canonical space of this continuous path space. And on the path space, the natural dynamics is the time shift maps. So you can you can shift your process forward in time by any amount. And and then we have also a family of parametrized measures where the parameters comes from some space, which we only assume is like compact metric space. and this family is is a family of invariant measures, and this is from the dynamical system point of view. But you can also think about this family as a family of S-value stationary stochastic processes, and their loss is given by this family of measures. So basically, we want to find out, like, when we have this model family, which of the parameter is the best one to approximate the observed system. Okay. So this is just the formal description. And then, as usual, we have the prior probability measure on theta. And then we have the loss function as described in the previous page. And we just develop our generalized posterior distribution, as also mentioned in the previous page, by integration of every parametrized measures on a state space, and then we integrate respect to all the parameters. So this is like the prior distribution on the space of parameters and the hidden states X. So in the previous page, we have the expectation over X, which is just like integration of this mu theta. But anyway, so the point is just the same as before. You have the exponential minus loss, and up to time t, and this loss up to time t in continuous time, what you have is like the integration of 0 to t, and the loss functions of apply to the dynamics up to time t. And if it's in discrete time, then you just have the summation of the loss up to time t. Okay, and just want to point out, and here we also have the normalizing constant, which will play a very important role in this work. And just write down the expression for that. It's just you replace this integral of E on parameter space with the whole parameter space theta. So this is the normalizing constant. And yeah, just to point out one thing here is that so you notice the notation here for the normalizing constant is pi, but the prior distribution is pi 0, because later on we want to sort of change this measures on parameter space so that we can prove the main result by looking at all the possible probability measure on theta. Yeah, just make a note of this. Okay, so after we give this precise formulation of our setting, so the problem of this is, do we actually have like posterior consistency as mentioned in the introduction? So do we know whether this generalized posterior distribution actually converges, or if it converges, does it concentrate on any subset of the theta? That sort of makes sense for posterior consistency. Okay. Okay, so then so the main contribution of this work, or maybe before I go into the main contribution, is there any questions on the precise setting? Okay, so I will move on. Yeah, so the main contribution of this work is to give a general framework of proving the generalized posterior convergence based on large deviation theory. So in the existing work of posterior consistency that I mentioned in the introduction, usually they are all proof for a very specific Bayesian procedure. Like it's very hard to see like what is the general approach to this kind of problem. If you change the system to a different system, then it's not clear like how do you change your proof techniques. And here we sort of give a very general approach to this problem based on large deviation theory. And we apply this framework to a class of continuous dependent processes on continuous state spaces called hypermixing processes. So in general, in the existing work of posterior consistency, people usually assume like one of the following, like they assume discrete time, or they assume processes of simple dependency structure, such as IID processes or Markov chains, or they assume like Gaussian processes, which is a very specific structure of the processes. Well, if they assume that, if they make assumption that the underlying process is dependent, they usually make additional assumptions that the state space are discrete. So it's only consisting of alphabets. So in this case, we sort of make the generalization of like all the things I mentioned above. So we are considering a class of continuous time dependent processes on continuous state space, and which is outside of current literature on posterior consistency. And then we also, just to show that how general our framework and proof techniques is, we also apply to a class of discrete time, discrete value dynamical systems called Gibbs process on shifts of finite time, which is a classical dynamical system, maybe in ergodic theory. And yeah, and then we don't just show that, well, maybe under some condition, the generalized posterior converges, but we also characterize the limiting generalized posterior by showing that it concentrates on those parameters that minimizes some expected loss and the divergence term respect to the prior. So this gives you the interpretation of the limiting generalized posterior in a way that it makes sense. So it actually converges to something that is sort of good in the sense that it minimizes some expected loss and some divergence. And we will make this precise later on. Okay. Okay. So now we're going to talk about the key part of this work is the large deviation framework and how to see the connection to large deviation. And yeah, the starting point is actually previous results of a preceding work by McGough, Mukherjee, and Nobel. So what they show is that suppose one can find a lower semi-continuous function that's defined on the parameter space, such that for any probability measure on the parameter space, one can prove this this limit. So this is like a asymptotic characterization of the partition function in an exponential scale. So this is the partition function, like the normalizing constant I mentioned before. So if one can prove the limit of as t goes to infinity, like -1/t log of the partition function at time t equal to the infimum of this function you just find, like v over all the theta on the support of this probability measure. So if one can prove this for any probability measure on theta, then one have the following conclusion. So if theta min is the set of minimizer of the function v you just found, then the posterior generalized posterior distribution will concentrate on the set of minimizer of this v. Okay. So the key point here is if one can prove this asymptotic characterization in the exponential scale for the partition function, then one obtains posterior convergence, and one can characterize the limiting posterior as it concentrates on the minimizers of the v you just found. So of course, one need to find what this v is, and so in the work of in this work, like the work of McGough, Mukherjee, and Nobel, they prove this characterization for a very specific dynamical system called Gibbs Gibbs process on chips for finite type, which I also mentioned that we will apply our framework to, but we were using a very different technique. But what they prove is for that specific system and using the techniques that's very specific for that dynamical system, it's not easy to generalize for that technique. Yeah, that's one of their main results. And the other main result is that they characterize for that particular system like what this V is. So actually, what they characterize V is has this following form. So if you input a theta to this function V, then it's equal to the infimum of the integration of the loss function at theta for some measure plus some divergence term at the measure respect to the product measure of the of mu theta and the nu. So this measure is minimized over all the possible. So in all the possible invariant measure of the system X and Y. Okay, so here the nu here is the underlying measure of the system Y, and mu theta is the one of the model process at theta. So basically, how you interpret this is so suppose you don't have any information on Y and X by how their relation. What is their relationship? What you can first guess is maybe they are just independent of each other. So they have the natural guess is they don't have any correlation or something like that. So you want to impose a prior distribution on X and Y. What you impose is just like the independent coupling. So it's the coupling of the mu theta on X and then the nu on Y. And then this is a prior distribution. And then actually it's a divergence respect to this prior distribution. So what you can interpret this is like a minimization over this integration, which is just the expected value of the loss plus some divergence respect to the prior distribution. Okay, and we will define this divergence later. It's sort of a divergence that's sort of specific to the dynamical system. So you may want to guess that this may be the KL divergence, the classical relative entropy. But since we are working with dynamical system, what we know is that if you consider the KL divergence of two maybe ergodic measure, because ergodic measures are either the same, like two ergodic measure are either the same or they are just mutually singular. So in that case, the KL divergence will either be 0 or infinity, which is like a trivial function, and it does not give any information. Here we have a divergence that's more specific to dynamical system, and it's a non-trivial function. We will see later. Okay, and yeah, just to give you because we will define this notion maybe in a moment, but just first to give you some impression like what this quantity is by giving you some example. So if we let K to be the usual KL divergence, and then just consider the simplest case when we have two IID processes like XT and ZT, and since they are IID, then their law on the path space is given by the product measure. Right? There's some some mu is some mu0, product mu0, and this is also a product measure. And if you consider this divergence term of eta respect to mu, which is like divergence on path space, then it boils down to the KL divergence of eta 0 and mu 0. So it's the underlying measure on one state space, just on S. Yeah, so this is how it does, how this divergence term do for IID processes. And if you consider a slightly more complicated example, maybe we consider xt and gt to be Markov chains with transition kernel P and Q, and they are stationary with initial measures like mu0 and eta 0, then one can sort of lift this initial measures and the transition kernel to a distribution on the path space. So that mu and eta to be the law of the whole process is on path space. Then if you want to measure the divergence of eta with respect to mu, then it becomes the KL divergence of mu0 product with Q, which is just you start with eta 0 as your initial distribution, and then you take a step with respect to the transition kernels, which gives you a measure on S product S, and then you consider the relative entropy of this measure with respect to the measure like mu0 product with P. So because for Markov chains, like the dynamics are captured by initial measures and transition kernels, so you can see that this H divergence actually like captures divergence of the dynamics between like Markov chains in this case. So this just gives you an impression of like what this divergence term does. Okay. Okay, so any questions so far? Okay. So now we're going to show you the key part of the work, which is the relationship with the posterior consistency, the posterior convergence and the consistency, and then the relation with Logitization principle. So recall that our main observation that's coming from the preceding work is that if one can prove this asymptotic characterization of the partition function, right, then one has the posterior convergence. So now the goal is to prove this asymptotic characterization of the partition function, where just as a reminder, like the partition function is given by this, that the integration of exponential minus loss up to time t, and respect to the prior distribution. And based on the previous results, we sort of guess like the V we want to find here has the following form. So it's the infimum or over all the invariant coupling of the expected loss, and then some divergence with respect to some prior distribution. So here is like the thing we have in mind. So the next thing is like how to reprove this characterization. Okay, so actually the key step is we can start with pi equal to the some direct delta on the single parameters. So here what we need to prove is for any probability measure on theta, but we can start with the single direct delta. In this case, for example, like the right hand side reduces to just a V of theta, right? Because the support of the direct delta is only like one single point. And then the partition function here, we can get rid of the integration over pi, because like when pi is the direct delta, then we only have the things inside with the single theta. So in that case, then we can see a connection with Logitization principle by the classical Real-Dimes lemma. Okay. So what is Real-Dimes lemma? So Real-Dimes lemma says that, well, suppose we have a function that's lower semi-continuous, and we have a process on some space that satisfies the Logitization principle with wave function I is equivalent to the fact that we'll consider any test function that's bounded continuous. Then we have the following asymptotic equality in the exponential scale. So the limit as t goes infinity, like 1 over t, the log of exponential, expectation of the exponential minus t, the test function f on the process gt is equal to the minus infimum over all the z's of the test function applied to z and the rate function applied to z. Okay, so this is the classical real times lemma. Well, I didn't tell you like what is large division principle in precisely, but since this is an if and only if statement, so you can take this thing to be the definition. But the goal here is actually one can prove large division principle with other techniques. But then if we compare with this equivalent characterization, then actually this one gives you the connection with respect to the posterior consistency we want to prove just in the previous page. Well, just by observing like this, like equality, this equation, right? You see the left-hand side is like limit of 1 over t log of some expectation of some exponential something. And if we go back to the characterization we want to prove, so it has basically the same form, right? The left-hand side has the limit of t equals infinity, 1 over t, the log of partition function. And the partition function is given by some integration with respect to some exponential, right? So basically, like the left-hand side here is exactly the same form. So now we only need to, what we need to do is just to pick the right z, the right space, the right process, and the right test function. Then we can exactly match the left-hand side of this with the left-hand side of the characterization. Okay, so just it's not important like what do we pick here, but just you can by matching them, you can not hard to work out like what is the correct thing to what is the correct thing to pick to match this expression. So here like we pick z to be just the probability measure, the space of probability measure on x and y. We pick zt just to be the empirical process, and then we pick f to be the integration that with the integration with respect to a measure using the loss function. So f is when you input a measure, then you integrate the measure with respect to the loss function. And then by plugging in this z, zt, and f to the left-hand side of the Real-Times lemma, then it just recover the left-hand side of the asymptotic characterization we want, at least for a fixed parameter theta. Okay, so it is not important that you need to see like exactly this works out, but you can just by comparing the expression, and you can figure out yourself like what should I put the f here and z here, etc. So now that we have matched the left-hand side of the characterization with the Real-Times lemma, then we also want to match the right-hand side, right? So again, in the previous page, we know that we sort of have the information that V has this form, right? It's an infimum over some expected loss and some divergence, which actually also looks very similar to the right-hand side of the Real-Times lemma. So if we pick f as here, like the integration with respect to the loss function, then f applied to z, which is a probability measure here, then this ft becomes the integration of the loss function of the measure, respect to integration of the loss function with respect to the measure you pick here. And you also have the infimum in front. So what you want is just to take the rate function, like I, to be the divergence that we want in the previous page. So basically what it says is that this V coincides with the right-hand side here. If we, by the Real-Times lemma, if this Z, what we pick to be the empirical process here, satisfies the large division principle with rate function equal to the divergence term we want. Okay. So just to repeat, the important point here is if we can prove that this empirical process satisfies the larger principle with wave function given by the divergence term, then by relativized lemma, which implies this equation, will gives us the asymptotic characterization we want here for a single parameter. Okay, so this is the first step toward the asymptotic characterization in the case of a fixed parameter. And many questions about this. And this is the main connection with large divergence principle and large divergence theory. So the advantage of this is that, well, there are a lot of processes we sort of know like how to prove large divergence principle in the existing literature, but there's not so much for posterior consistency. So by looking at this connection, then one can expand like more process for posterior consistency using large divergence techniques, yeah, to prove. Okay, so now I think now what we can do is maybe to give a precise definition of what is this wave function, what is this divergence terms, what is the precise definition. So this also comes from large divergence theory. So if we only consider X here, like the model processes, if we assume they are very well behaved, like IID or some Markov chains, then it's actually well known in large divergence theory that the empirical process of like this empirical process satisfies the large divergence principle with wave function given by this divergence terms. And this divergence terms mathematically is given by the following definition, which is called the relative entropy rate. So it's defined by the following: if we have like two measures on the path space, then the relative entropy rate of lambda with respect to eta is given by the limit as t goes infinity, like 1 over t, the relative entropy, the classical relative entropy, applied to lambda and eta, but restricted to the sigma algebra up to time t. So you only restrict your measure to the path up to time t, and then you can measure the relative entropy of that, and then you take 1 over t and take t to infinity. So this is actually a classical result in large divergence theory for process like IID process and Markov chains and maybe even hypermixing process. So in that case, we actually get the inspiration about like what this H should look like. So how is this H formally defined? Is given by this relative entropy rate. Well, I think in the statistical mechanics literature, they call this the average entropy production or something like that. Okay. Okay, so yeah. So now that we know how to define this relative entropy rate on X, but recall that we actually want to define it for the product like of X and Y, and then we just expand this definition, which actually appear in one of the work in large divergence literature by Timo. And what he does is that for measures on X and Y, then we still have the same limiting definition of this relative entropy rate, but we change the sigma algebra to include the space Y. So for space X, we only have the sigma algebra up to time t, but now we include the whole sigma algebra of Y. So again, because we don't assume any structure on Y, but we assume X is a path space. So in that case, the nice thing about path space is you have this nice partition of the space by this sigma algebra up to time t. but in general, you don't have this kind of nice partition for general dynamical system. So actually, yeah. So in summary, to prove the asymptotic characterization for fixed theta, what we want to show is that the empirical process for x and y satisfy the large deviation principle with the rate function given by the relative entropy rate on x and y, and this relative entropy rate is defined like just as above. And yeah, and actually for this is also like studied in the large deviation literature, just as the case when you only have x, and this is called a conditional or quench large deviation principle. So what it means is like when you fix the y here, which you can think about this as the like condition on y or condition on a random environment, then you look at the large deviation behavior of the empirical process, then actually this is called the conditional or quench large deviation principle. And this result is proof if we, at least in the case of nice Markov chains, which is coming from the same work where they define this relative entropy rate. And yeah, and actually in this work, we also extend part of this work to include like examples like not just Markov chains, but like hypermixing processes. Okay. Yeah, so now just to repeat again, if you want to show the asymptotic characterization for the posterior consistency, we want to show at least first for fixed parameter is that we want to show the large deviation principle of this empirical processes. And to show this, you can refer to like maybe classical literature to learn the techniques for large deviation principle. And the important thing is like the connection of large deviation principle and the posterior consistency. Okay, so yeah, before I move to the next, so yeah, so the next step is, well, here is for fixed theta, but again, just recall that for the characterization, we need to show that for any distribution on theta, right? But before that, let me just like give you maybe more example of the relative entropy rate. So if you consider diffusions, like stationary Ito diffusions like of x and y, x and z, and then you want to study like what is the relative entropy rate between these two on the path space, right? So if mu and eta is the law of these two processes on path space, then the relative entropy rate is actually given by like 1/2 of expectation of some matrix norm of A minus B squared. So A here is A and B are the drift here. So again, this divergence terms actually like capture some of the dynamics of the processes on the path space. And if you are a person from maybe ergodic theory, then you will probably know like the shifts of finite type. And if you consider X to be a shift of finite type and sigma to be the uniform product measure, then any measure that the divergence of any measure with respect to the uniform measures is given by the log of the number of alphabets, number of letters in your alphabets minus the entropy of eta. So where the entropy here is like the classical Kolmogorov-Stein entropy, or the measure theoretic entropy. But anyway, just this is an example for the people in ergodic theory. And yeah. Okay, so okay. So like any questions so far? yeah, well, basically the details here is not very important, but hopefully I can convince you the impression that like the connection between posterior consistency and large Bayesian theory. Okay, so the last step is just what we show is already what we showed before is just how to connect in the case when you only have a single parameters, the asymptotic characterization with the Dynamics lemma. So to prove the whole characterization, we need to work out a strategy for showing the characterization for any parameters in the support of any measure. So basically, let me just intuitively say like how to do this. Well, we'll recall that for single parameters, then we want the large Bayesian principle to hold for the empirical measure for a single parameter of x and also y, right? So now we are considering a mixture of this model family with mu theta given mixing by just any measure pi, right? Then we also want to minimize the maybe like the right hand side, the v over all the parameters on support of pi. So intuitively, what we want is like a process level large Bayesian principle, which is like the large Bayesian principle of the empirical process of this mixture of mu theta with rate function given by the infimum of theta or the support of I theta, where I theta is the rate function for the mu theta. Basically, just by comparing the characterization, on the right hand side, we want to take the inf over theta of the support, and the relative entropy rate is the rate function here. So we also want to take the rate function to be even over theta on support, like intuitively, right? Then actually this is connected to another thing that is so well studied in the large division literature. It's called like the annealed large division principle or large division principle of mixture. So what it does is that once you have a large division principle for any single mu theta, then you can also derive a large division principle for any mixture of this mu theta. And the rate function is actually exactly given by something like this. So it's something like the infimum of theta on the support of the measure that give you the mixture. And to show that, and one property to verify in some kind of continuity. So it's like you want to show that some minimization over some sets, and then what you want is actually some kind of continuity of the map. So the key property is the theta of mu theta is actually exponentially continuous. So in the interest of time, just like maybe I don't go to the exact definition of this, but you can find this definition of exponential continuous in this classical work of large division of mixture. Okay, so yeah. So let me just skip maybe just briefly talk about the assumption we make on the loss function. So basically, we make the assumption that more or less like the loss function has a form of this. So it's given by some metric between some projection of x onto the y space and measure it with respect to the sample we have on y. And we just assume that the metric is bounded. But you can truncate any metric to get a bounded metric, or the projection mag is just uniformly continuous, which is in a way is a natural first assumption that you can make for non-compact state space. And then our main theorem can be stated in the following way. So if the family, like the map, the parametrization map from theta to mu theta is exponentially continuous, then we can prove that the V we get is continuous, then also we have our desired asymptotic characterization for posterior consistency. So by the previous results, they are mentioned at the first step of the observation, then this will imply the posterior consistency. Okay. So to summarize, which I think, yeah, it's almost 1 hour. It's a good place to stop. So in summary, the message I want to convey here, like despite all the technical details, is that like, so we sort of develop a framework to prove posterior consistency that's quite general, and the guiding principle. So the framework is also very flexible, and so we just want to give you like the guiding principle for that is just if your model family has good large division behavior, for example, like IID microprocesses, like hypermixing processes, or many other well-behaved dynamical system, they all have good large division behavior, then we have hope to prove like posterior consistency, which means like the generalized posterior concentrates asymptotically to those parameters that minimize the expectation of the loss plus some divergence term. And how to do that is that, well, the first step is because you know that like the mu theta has good large division behavior, the empirical process of that has good large division behavior, then you can first extend those large division behavior to a quench large division principle. Just you expanded the X with a fixed random environment Y, and prove the large division principle for the empirical measure of this by extending maybe the techniques they use to prove the large division principle of just X. And then the second step is to show exponential continuity of the parametrization map with respect to the loss function. And once you do this too, then you can prove the asymptotic characterization, and which will imply posterior consistency. Okay, I think this is yeah, the main part of the talk. So if you are interested, I can show you some examples, but I think I can just
please go ahead. I think just go ahead, give some examples. I mean, I told you before that there's no time limit on the seminars.
Okay.
Yeah.
Oh, maybe before that, like, any questions? Yeah. Okay. So again, like the main message is just these 3 steps. And the important thing is to see how posterior consistency is connected to large division behavior. Okay. So okay, let me just briefly talk about the examples I have here. And okay, so the first one is hypermixing process. So we applied this framework to prove posterior consistency when the model family is consisting of like hypermixing processes. And here's the hypermixing process which is defined here. So why do we pick this kind of processes? As mentioned in the introduction, they sort of falls outside of the current literature of posterior consistency. And also this is something we know that it has very good large division behavior because of the classical work of like these people. So yeah, the definition here is not very important. Just we know that it will work. The large division principle will work out this case. So pick these processes. Let me just go over it. So yeah, a measure like mu on the path space is called hypermixing. So if there exists some alpha which measures the mixing constant, and we satisfy like alpha L equals 1 when L goes to infinity, then the product of any function f1 to fn, which are measurably separated. So they are supported on like different segments, disjoint segments of the time interval. Or like most precisely, like they are like f like I1 up to in measurable, where I1 and up to in they are like distance like L apart. So basically, like they don't see each other. So if the measure is independent, like IID processes, then this is just equal to the product of the norm of this measure, right? And the norm of these functions, the L1 norm of these functions. But it's hypermixing, so it's not exactly independent, but it's sort of still like mixes a little bit, which we can describe by this inequality. Like it becomes upper bounded by the product of some norm of each of the function, and this norm is very close to 1, so it's like almost independent. But you have some space to work around it. But anyway, so this definition is not important. Maybe that and I will show you some example in the next slide, a concrete example in the next slide. But the thing here is, if you want to prove exponential continuity of this map, which is like the second step of our proof framework, then usually what we need to assume is like this map is continuous with respect to the weak convergence, and also alpha theta here, like this constant is sort of upper bounded, so it does not get like arbitrary slow of mixing. But anyway, so this sort of natural assumptions that you get to prove a posterior consistency. And the concrete example of this is, for example, the IID obviously is one of them. And the other ones are hypercontracted Markov processes. So basically, if you have a Markov semigroup, then the measure is hypermixing if like your semigroup is hypercontracted. And in this case, it just means the operator norm of like L2 to L4 is 1. And this is actually a very well studied property. It has many connections to other property in Markov processes. For example, it's basically equivalent to the log Sobolev incurred. So for that, one can find like any other criterion to prove this, and so verify the hypermixing property for Markov processes. And one can also like relax the dependency structure a little bit. So like Markov processes is sort of refer to the processes with a simple dependency structure, like the current time steps only depends on maybe the previous one. But one can expand this to the dependency for not just one time step, but a segment of time step. So basically, so basically one can define a semigroup, which is called for absolute Markov processes, such that if you apply to a function at time t, then it's like expectation of the time shift map t conditioned on the past segment of minus epsilon. So intuitively, it just says the current state depends on the previous epsilon segment, just not just one time step, but a segment of time steps. And it also holds for some Gaussian processes if you assume some decay on the spectral density matrix. But all of this can be found in the classical large division paper for hypermixing processes. And probably a book, a book on large division too. Yep. Okay, again, so this example of hypermixing processes is sort of outside of the current literature for posterior consistency. So we include that to show the power of our framework. And the second example, like the Gibbs process on shifts of finite time, this one is sort of proved by the pure results I mentioned that gives you the asymptotic characterization. But we include this to recover the previous results and also to show the flexibility of our framework. And so let me give you briefly describe the definition of here and show and tell you a little bit about the proof technique. Well, basically it says that if you so what is shifts of finite type? Basically the state space is finite, so it's consisting of alphabets, and then you look at the path space, like the sequence space consisting of values from this alphabet, and then that dynamics here is the shift map, so you can shift your sequence just like a stochastic process. And then what is a Gibbs measure, which basically means that if you look at like cylinder sets, if we look at cylinder sets of this form, so which means like you look at those sequences with the first coordinate equal to x0, the second one equals to x1, and etc. Then if you measure this cylinder sets, then it's almost exponentially, so it's like equivalent to an exponential of some constant which called pressure times t plus some partial sum of some phi applied to shifting x. So this partial phi is something called the potential. So this measure is called the Gibbs measure with respect to the potential phi. This is like a classical system in algorithmic theory. And yeah, and actually it includes like finite states Markov chains with arbitrary dependencies. And then, so what we did in this case is, so in the previous case we solved like for the hypermixing processes, we solved directly prove the Logitization principle by adapting the classical proof from Logitization theory. But in this case, we did not do that. We did not directly prove the Logitization principle, but we were using this structure of Gibbs measure by reducing it to an IID case. And this technique is actually very common in Logitization theory. It's called like exponential tilting. So one can like reduce measures of this form, like measures of something that multiplied by some exponential of the IID measure. And then by using exponential tilting, you can reduce this kind of measure to IID case, which makes the proof like very simple. And also, also support the fact that our framework is like very flexible. Okay, and actually there are a lot of, I think there's other interesting techniques that get used in the proof, but I don't think I need to go into detail right here. And yeah, and then the criterion for exponential continuity for discount processes is the same as the previous results. We just need to assume that the potential, the parametrized family of potential is actually continuous. The map is continuous with respect to maybe some holder class. Or the Gibbs measure here is unique with respect to any potential. And then when we have this continuous parametrization of potential, then we also have the exponentially continuous parametrization of the family of Gibbs measures. Yes. Yes.
Yeah. Can you explain what you mean by exponential tilting?
Oh, yeah. So in Logitization, then well, so basically it's just when you have a measure, like for example, IID measure, right? Then you know have good Logitization behavior. Then you want to prove it for a slightly different measure than IID, and the difference is given by you have an IID measure, but you integrate respect to some exponential minus some potential, which change your measure a little bit. But then because of the exponential plays very well with the scale, then you can sort of reducing back to the ID measure. Something like this.
Okay.
I think you can maybe I think a textbook in large Bayesian theory did a better job explaining this than me. Yeah, and also you get the rate function very directly from the exponential tilting. It's like a formula that you can, when you have this form of measure, then you can have this form of rate function. You don't need to figure out yourself. Anyway. Okay, I think I'm done here. And
all right, thank you.
If you have more questions.
Yeah, any other questions? All right, seems that there are no questions. Yeah, thank you very much for the talk. And thank you everyone. Take care. Bye-bye.
Thanks.